Hey guys, welcome to Chapter 53. Chapter 53 is all about population ecology. I am pretty amazed at how quickly this year has gone by. It seems like it's gone by pretty fast. I really appreciate all the hard work you guys have put in. I know doing this course online, particularly this biology course, has been a bit of a struggle. Not perhaps the way that we wanted to do it. I would have preferred to have been there on campus with you, but most of the students have done very well, and I think if you've been a responsible person, you've kept up with the videos online and contacting me via email and through the Schoology website, then you have probably done okay. So we only have a few more chapters to go. Chapter 53 is all about population ecology, and this kind of gets to some of the question as to why some creatures have huge population swings up and down, or why, for example, some creatures are doing fine and others go extinct. For example, why is the population of endangered species such as a rhinoceros or tigers or polar bears, why are their populations in such flux and diminishing? And then why are there other creatures like, say, rats, mosquitoes, cockroaches that seem to be doing just fine in our modern world? So we're going to talk a little bit about what's called population ecology. And if you've been thinking that there just hasn't been enough math in this course, well, you're in luck, because this chapter does have a little bit of mathematics, a little bit of formulas involved, but we'll try to keep it simple. Remember that we are more about the concepts. This is not an entire course in population ecology, so we won't go into quite a bit of depth, and we will try to stick with the concepts and the ideas. We do want to know the formulas and understand what those formulas mean, but I wouldn't ask you to memorize the formulas. If I ask you any questions on the test, I would provide the formulas. You would just need to know how to use them, and to do that, of course, you would have to understand them. So we're going to talk just a little bit about how populations vary. We're going to talk about growth rate, we're going to talk about birth rates and death rates, and we will even kind of segue that into talking about the human population and the fact that our Earth has right now already over 7 billion people, and then getting into the question of what is the carrying capacity of the Earth as far as humans is concerned. Is it 7 billion? Is it 10 billion? Is it 100 billion? Are we running out of space and food and the things that we need? Or are we doing just fine? And how have we changed the world to allow for these 7 billion people? So that's what we're going to be talking about. We'll get started in just one second. In the overview for this chapter, your textbook uses the example of a particular type of study that's been done on some sheep, and it says there's a small population of a fairly rare old breed of sheep called soy sheep. Soy sheep were introduced to this particular island called Herta Island in 1932, and on this island they basically have no predators. They have a plentiful food supply. They have everything that they need for a healthy population, and so this is an excellent place for scientific study to occur. And this population of sheep that was introduced to this island in 1932 have actually been under scientific study for over 50 years now, and this again provides sort of an ideal situation to watch the population size change over time and to measure that population size and to look at the factors that affect that, because there's fairly abundant food and virtually no predators on this island. And you would think, well, that would mean they would have a huge population and it'd probably be very stable. But in actuality, the population does kind of go up and down, sometimes quite a bit. Sometimes it swings dramatically as much as 50% down or 50% up. So the question would be why? And that question of why is a question of population ecology. So when we study the varying populations, the ups and the downs, the birth rates and the death rates and the factors that affect that, that's what population ecology is all about. There is a great crash course video, so make sure you take a look at that. There's actually 2 crash course videos. One of them focuses on non-human living creatures, and that's probably more applicable to this chapter. And then the other one actually is more applicable to the very end of this chapter, where we talk about the human population as well. So we could study the human population ecology just as we would study, say, the population ecology of these soy sheep or of a grove of oak trees or something like that. So the definition of population ecology is here on the page. The study of populations in relation to their environment, and that would include all the various environmental influences that affects that population, the density and distribution, the age structure, population size. These are all factors we're going to take a look at with this chapter. Let's get started with concept 53.1. It says dynamic biological processes influence population density, dispersion, and demographics. So there's some words we're going to need to know, of course: density, dispersion, demographics, dynamic biological processes. So these are ever-changing processes, and we don't usually see a lot of static population in biology. We often see populations that rise and fall over time depending on what's going on in the conditions, environmental conditions around them. So a population we've already studied before is a group of individuals of a single species living in the same general area that tend to interbreed with one another. Populations are described by their boundaries and by their size. And sometimes it's distinctly clear as to what a population is, and sometimes that's kind of just a man-made designation as far as a particular population. So if we were going to look at, say, pine trees in a East Texas forest, it would be difficult to say, okay, this is the population of pine trees. We might just say in, say, this particular county, and we would deem that the population, even though there are pine trees in the surrounding counties as well. Sometimes the population is not clearly defined, and we kind of define that as part of our study. Other times you might look at a particular population that is already clearly defined, like this population of soy sheep on this island. Well, that's it. The island is of a fairly small size, and there's only one group of sheep, and they're not going to move around to other islands, so that population is easily naturally defined. Let's talk about some of these other words, including density. Density is the number of individuals per unit area or volume. So we could be talking about something like number of oak trees per square kilometer in a forest area. Or we could be talking about something quite a bit more tiny, such as the number of E. coli bacteria per milliliter of a fluid that we have in a test tube in the laboratory. Dispersion is the other word we talked about. It's a pattern of spacing among individuals within the boundaries of the population. So how are these separate creatures spread out within their range or within their area? And there's actually 3 different ways you can be dispersed, and we'll take a look at that in just a second. The other thing we want to talk about is with density. When we are trying to measure some of these things, you got to think that we are, for the most part, measuring wild creatures. You can't just go out there and see all of them at one time, or walk up to them and count them. If we're measuring the density of oak trees, well, that's pretty easy. But if we're measuring the density of white-tailed deer within that same forest, that's going to be a bit more difficult. So it becomes almost impractical or impossible to count all the individuals in a population. So we have a couple of different methods for dealing with that. We have what we call sampling techniques, and sampling techniques basically allow us to estimate with pretty good accuracy the density and the total population size of a particular creature that we're looking at. So if we want to measure, say, the population size or density of white-tailed deer in all of the county where I live, in Smith County, well, there's no way we can possibly find and count all of those deer, so we're probably going to do it a couple of different ways, and we will actually use 2 or 3 methods and kind of use the numbers from all of those methods to come up with a more accurate population size or density. One of those that we might do is we might extrapolate from small samples. So we might be able to count all of the deer that we see in one small area in one night. And we do these small samples throughout the county, various times, various places, and then we can kind of extrapolate from those small samples out to what the entire population might be. Another way is to index the population size using other kinds of markers. Like we might count, say if we're looking at birds, we might count the number of nests that we find, or if we're looking at bears, we might count the number of dens or the number of piles of scat, or if we're talking about deer, we might try to find all of the various tree markings and rubbings where they rub their antlers. So we might use some sort of evidence for the animals to help us estimate the number and density of those animals. Finally, we might use a method that's oftentimes used in scientific study in ecology, is what's called mark and recapture method. The mark and recapture method is one that we might use, say, for dolphins in the open ocean, or birds, or any sort of creature that has a bit of movement and that would be impossible to kind of track and count any other way. With the mark and recapture method, what we do is we capture and tag with some sort of, oftentimes nowadays with a GPS type tag or a radio beacon type tag, and then we release that individual back into its population. And the thinking is we're going to give that individual time enough to mix back in with the general population. And later we're going to go out, we're going to recapture more of those creatures, and we're going to see, do we recapture any of the ones that we've already tagged? And using that information, it will help us come up with an estimate of the total population size. So here's where a quick little math formula comes in handy. So we're going to be measuring N. That's our estimate of population size, is N. And the way we do that is we take first the sample of individuals in the population that we initially tagged, so that would be the number that we initially tagged, multiplied by the recapture number, the number of samples of individuals that we captured the second time, and then divide that by the number that were already pre-tagged. So we're going to capture twice. S is our first capture, N is our second capture, and then we're going to divide that by the number of those between the two that were captured twice. So when we go out to catch the second time, if we catch a bird that already has a tag, or we catch a dolphin that already has a tracking collar on it, well then that is going to help us come up with a ratio, and we can estimate the total population from the mark and recapture method. The example used in your textbook was the study of this particular type of dolphin, where they would mark and recapture, and then they would estimate the whole population size based on the mark and recapture. Now there's a couple of things you have to keep in mind. This is we really feel like the mark and recapture is only accurate if you give the marked individual time enough to go back and distribute itself evenly amongst the population. You have to assume that there's not a lot of immigration and immigration in and out. You have to assume that it's completely random as to which creatures you're going to capture. In other words, you would like to think that every time you go out to capture dolphins, it's just going to be a completely random possibility as to whether or not you capture one that's already been tagged. So if you take those into account, you get a fairly accurate number. But if there are other things that affect that, like for example, maybe there are some dolphins that are just more friendly to humans than others, and they tend to be the ones that get captured over and over again, well, that might start to skew your data just a little bit. So you have to make some assumptions, and with those assumptions, then you can probably get a decent estimate of the population density or size using mark and recapture. One of the things that we said that can skew our mark and recapture data is whether new creatures come into the population and other creatures leave that population. So if there's a lot of travel, a lot of inflow and exit flow, well, that is going to kind of skew our data just a little bit. So density is the result of this interplay between exiting and entering, because for example, if we're talking about dolphins, not all dolphins always stay with their same pod, particularly males. Once they start to get older, they may go out on their own, join another pod, form another pod. Females tend to more stay within their family grouping over a longer period of time, but it kind of depends on the species and the situation. So we need to talk about two different words, inflow and outflow. Immigration with an I is the influx of new individuals from other areas. So when creatures come into a population, or think about when humans come into a country, like humans immigrating to the United States from another country. So immigration with an I, so think I for in. And then the opposite of that would be immigration. Immigration with an E, E for exit. Emigration is the movement of individuals out of that population. So let's say a U.S. citizen emigrates to Canada and goes to live in Canada. That would be emigrate with an E. So these two factors affect the density and the total population size of any group of living creatures. So here's a great illustration kind of illustrating some of the main factors that affect a population size or the population density. So here you have the population of these little birds right here in the middle, and the factors that affect this population would be the births. Of course, births add to the population. The flip side of that would be deaths. Deaths take away from the population. We also have immigration, coming in, birds from other areas that come and join this group. And then we have emigration, birds that leave this group to go elsewhere. So these are kind of the four factors. You have births and immigration add to the population, and deaths and emigration take away from the population. Okay, let's take a quick break right there before we make this video too long. In a second, we'll come back, finish up concept 1, and we'll talk about things like patterns of dispersion and a few other things that apply not only to all living creatures but to humans as well. And so we'll take a quick break, come right back.